So our next topic, that kind of bridges us to our next topic, finally, refractive FIR. And just a bit of preview. Today, we start by talking about, we start from ideal low-pass filter. We'll start from ideal low-pass filter, and then we'll talk about the method of window. Or I should say the window method. Okay, so then we talk about touch base on the window method. And probably on Thursday will be April the 25th. On Thursday, we'll probably talk about choice of windows. What kind of windows shall you use when you want to design your filter to satisfy certain specs? Okay? So we compare it between the performance of different types of filters, or different types of windows. I'll focus on low-pass design first. Okay? And probably sometime next week will be actually we'll probably talk about Kaiser family windows. Turns out that there's a family of windows parameterized by data parameters, such that you can trade off between two important specs. That one of them is the transition bandwidth, the other is the height of the ripples. Okay, ripple of the cover line. And probably that will be the end of the range. We'll cover the range of our midterm. Okay, the range of our midterm is going to be all the way to until next Tuesday. Okay, so I promise you that. And that's probably going to be the end of our second midterm. It's going to be, we'll cover all the way to whatever we cover till next Tuesday. Okay. So that's kind of the preview. Okay, so now we are entering this new topic of designing the FIR filter. Design of FIR filters by windowing. And this part is in the section 7.5 in the text. Okay, so let's recall the ideal low-pass filter. Okay? An ideal low-pass filter is the goal of our design. We want to have a low-pass filter. And what does low-pass? What does filters? What does the word filter mean? Filter. When a filter keeps something and lets something go, we let something pass, right? Such as a coffee filter. You keep the powder and let the coffee with the fluid drops. The filter, right? So the filter, ideally you want to keep all the coffee above the filter and let all the coffee powder. You want to keep all the powder and let all the fluid drops, right? So ideal filter keeps everything below the cutoff frequency. And just, I should say anyway, you know what I mean. The let all the ideal low-pass filter has a gain of unity for the pass band, and anything that is above the cutoff frequency should be zero. The gain should be zero. By anything I mean from omega c to pi, okay? We're talking about digital filters. So that's our ideal response. And for the negative frequency from 0 to minus pi, there's a signature. going to be extinguished over here. So this is, suppose that this is the desire of our frequency response. Well, the pass band between minus omega c and plus omega c being the total frequency and 0 elsewhere. This is ideal. Ideal low pass filter. So we know that ideally the outbound our desire. Let me check our notation. Ideal low pass response. Okay, LP stands for low pass. Okay, the ideal low pass response should be 1 for in the pass band and 0 elsewhere. Elsewhere. So therefore, let's make that derivation. So this is the ideal low-pass response in the frequency domain. So for designing a filter, we talk about what happens in time domain. Okay, we want to calculate the impulse response. So we know that the impulse response corresponding to this ideal low-pass response, the ideal low-pass filter, here LP stands for ideal low-pass filter. Okay? It's going to be the inverse DTFT of this function. The inverse DTFT, let's just review it. There's a 1 over 2 pi, and you integrate h of LP e to the j omega. We will synthesize the result by multiplying this with e to the j omega n, and just integrate over all omega from minus pi to pi. Okay, so that's just a definition of inverse DTFT. It's going to be 1 over 2 pi still here from minus pi to pi. And now note that HLP, the response is 0 outside the pass band, right? So we can replace with the range of integral to, we can just integrate from minus omega c to omega c, 1 times e to the j omega n. Integrate that over all the frequencies in this range. So that's good. And the result is pretty, should be pretty familiar by now. The result turns out to be sine of omega total frequency times n divided by pi n. Divided by pi n. For n not 0. Okay? For n not 0. And at n equals to 0, we have the results to be omega c divided by pi. N equals to 0. Okay? So far so good? So we know that this ideal response has an impulse response. The ideal low-pass filter has an impulse response that lasts forever. It has an infinitely long tail on both sides. And so on and so forth. It's going to be lasting forever. Okay? And because it lasts forever, it cannot be improved. So this is the ideal impulse response of this low-pass filter. The impulse response of this ideal low-pass filter. It's going to be long. It's going to be lasting from minus infinity to infinity. That cannot be improved. Okay? And in particular, it's also not going to be causal, right? the negative time part all have values, okay? So everything for n less than 0 is not causal. So do observations. First issue is that it's not causal. It's not causal and it's infinitely long. So these two properties make it, we should realize that because of these two properties, this filter, ideal low-pass filter, can never be realized. It cannot be implemented. So what should we do? So how should we do to change this situation? How can we do differently? Probably less ideal. So here is the suggestion. So here's where the window method comes in. So here is the idea of our design. Okay? Our design is a lot about guessing, about compromise. How do we make compromise? The idea now of our design is, okay, so we look at this sinc function. By the way, this is the sinc function. Okay? This is the sinc function with the factor omega c inside the sine part. Okay? If we look at this sinc function, let's claim that maybe most of the energy is concentrated in the middle, near n equals to 0. And maybe all the energy is kind of concentrated near time 0. So let's try to just, this is my suggestion. Okay, let's just focus on the middle part. Maybe we will just keep the middle part. Maybe we'll just keep the middle part from time minus n to plus n. How about this is our design? Very simple stuff. Let's just keep the middle part. That's essentially the idea. Okay? How about let's just keep the middle part? Would that be optimal? Okay, so let's keep the middle part. Okay, so idea is our two steps. Step 1, keep the middle parts. So when we keep the middle part, that means that for everything outside the range minus n to n, we're going to just ignore it. We're going to just forsake, we just abandon, we're going to throw away anything that's outside our range of interest. Okay? We're going to sacrifice it. That's our idea. In other words, we will sacrifice. We'll just ignore, sacrifice, we'll just delete, erase, we'll just abandon, forsake. We'll just tossing away. Okay? Everything that's outside minus n to n. Sacrifice anything outside minus n is the range of minus n to n. So that's the first one. Okay, so the first step kind of solved our second problem. Now after throwing away everything outside the range minus n to n, we already make it, now the result is no longer infinitely long. The length of our filter becomes finite. Okay? By throwing away all the tail part, by throwing away the tail part, the result becomes finitely long. So that is a good first step. And secondly, but now strictly speaking, now if we keep the part from minus n to n, still strictly speaking, this filter is not causal yet, not yet causal. Because for the negative time part, from minus n to minus 1, we still have some non-zero values, or non-zero samples. So strictly speaking, this filter is not causal yet. So what should we do? Just simply shifting the filter, okay? Shift to the right. So the second step is just to shift to the right. Shift to the right by how much? By n samples. We define our time axis. Okay, we define the origin of our time. So after shifting our equivalent, we are shifting the time axis to the left by n samples. Now the new time index is going to be 0 for the first sample, and n in the middle, and 2n in the end. Okay, so that is to say new time. Let's denote the new time as n prime. Okay, so we're going to say shifting to the right by n sample, or equivalently, we're going to say combining these two steps, we're going to say this is the result of our design. Okay, so combining these two steps, the result of our design in terms of the original low-pass ideal response is going to be as follows. H of n is going to be n minus n. All right. For 0 from 0 to 2n at 0 elsewhere. So this is the result of our design. Okay, the relation between our design and the ideal response. First of all, we are going to just keep the middle part. So by ignoring everything, the tails. Okay, outside the range of minus n to n, we're going to set it all to 0. We set it all to 0 to make our response finite. And then also we shift to the right by n, okay, to make it causal. Abandoning the tails to make it finite, and shifting to the right to make it causal. So these are the thoughts behind the two steps. Any question here? Any question here? So the result of our design, if you will be still be the same, basically the same thing. We're not going to change anything, okay? We're not going to, at this point, we're not going to change anything in this range. But then, for time 0, right here, and time n, right here, time 2n, right here. That's the result of design. And this filter has a length of 2n plus 1, okay? And it starts from time 0, for sure. Another question is that certainly this is not going to be ideal anymore. This is not going to be ideal anymore because we have abandoned the health. Right? But how much? The question is, how much does it differ from the ideal response? We want to design a low-pass filter, right? But after our claim that this is a design, then you should ask me how good is the performance. How much does the values response differ from ideal? How much does it deviate from ideal? That's the question. Yes. Yes. Right. And plus, you need the plus. Let me see. So for n equals to 0, we'll just check this. So this is going to be HLP, the ideal load path response taken at time minus n. So this is our starting point. Okay, now thank you for doing this one. We also make sure that plus sign or minus sign is consistent. Okay? So we have to make it causal, we have to make it finite. But then the question is, how much does this filter deviate from ideal? How far is it from ideal? Hopefully not too far. Okay? So the question, big question. How far is it from ideal? how far does the magnitude response deviate from ideal? Okay, so to answer this question, we will introduce, but essentially I want you to know that essentially what we mean by keeping the middle, or equivalently, you can think of it as if we are multiplying the ideal response by a rectangular window. Let me say that again, okay? Actually, equivalently, what we're doing here is to multiply the original ideal response by a rectangular window. So let me clarify what that is. So or equivalently, our first step, what we do in step 1 is we have an intermediate result, okay? Let's say the intermediate result is, let's say this is G of n. Step 1 gives us the intermediate result G of n is equal to the original ideal response times a window function. And that's why this design method is referred to as the window method. Because essentially we are doing nothing more than multiplying our ideal response with a window. We keep only the middle part. Okay? Keeping only the middle part, we are multiplying the ideal response with a window function where Wn is 1 from minus n to n and 0 elsewhere. That's the result, the intermediate result of keeping the middle part. Or equivalently, by keeping the middle part, we are multiplying our ideal response by a window function. In this case, the window function is the rectangular window because the constant 1 is that range. Okay, is that range. But step 2, shifting to the right, is very simple. So shifting to the right, so the result of our actual design is G of n shifted to the right. Okay? So let's now just kind of separately consider step 1 and step 2. So to answer the question, how far is the result from ideal? So we can answer this question. We can answer this question by separately thinking about the effect due to step 1 and effect due to step 2. We will separate, so what coming up next is to separately consider the effect of step 1 and step 2. Okay? Any questions so far? We're going to discuss the effect separately for step 1 and for step 2. Okay? Step 1. So step 1 is essentially a multiplication in the time domain. Right? Multiplying the ideal response with the window. So we know that there is a kind of convolution theorem of the second kind. But we used to talk about what? Multiplication in the frequency domain is convolution in the time domain. Right? But now we have a multiplication in the time domain. And briefly speaking, the result is convolution in the frequency domain. Convolution in the frequency domain, in frequency. Okay? So that's the result, the effect of step 1. Now we are multiplying the ideal response with a window function in time domain. We should expect the magnitude response to differ from ideal because of convolution. Because of the convolution that's happening in the frequency domain. Okay? I will come back to this. But the second step is easier, actually. For the second step, we're just shifting everything to the right in the time domain. And we know that there is shift theory, right? If we shift everything to the right in the time domain, in the frequency, what happens in the frequency domain? There's going to be an exponential term that happens in the phase, right? So in the frequency domain, we are going to multiply the frequency response by this phase factor. Is it minus j omega n? N being the amount of shift. Okay? So that's pretty clear. In the frequency domain, the corresponding effect is a change in slope in the phase response. Here, this is not going to change the magnitude response. Since the shifting. Okay? Alright, so now if we separately think about step 1 and step 2. Let's focus on step 1 first. Because step 2 is easy. for that, let me just keep my drawing over here. Okay, this is the ideal response. That's the ideal response. Now we'll take a look at what exactly is convolution in the frequency domain, and how would that change our magnitude response because of convolution. Okay, so this is our ideal response. And now, in the process of our designing, we have multiplied, in the first step, we have multiplied our ideal response with a window function, a multiplication time domain. So therefore, step one, because of step one, we expect, or more explicitly, what happens in the frequency domain is as follows. Let's say, if G and M in the Fourier transform, if the DTFT of G and M is denoted by G of E J omega, right? This is our notation so far. It turns out that multiplication in the time domain results in convolution in frequency domain, and the result the resulting spectrum is going to be expressed as a convolution. So I'm going to show you the convolution. Okay, the resulting convolution is going to be an integral. We will take the low-pass ideal response, e to the j omega, and there is integrand theta times big W of e to the j omega minus theta. And we are going to integrate with respect to this bounding variable theta from minus pi to pi, and there is scaling factor. That's the convolution theorem of the second kind, okay, where big H subscript LP stands for the ideal response, and big W stands for the DTFT of the rectangular region. Okay, multiplication in the time domain, convolution in the frequency domain. So now omega omega. This should not be omega j. Wait. JC. JC. Okay, so that's simply the result. Okay, this is a theorem actually. For anything, any two signals that multiply in time domain, their spectrum are going to be convoluted, convolved in the frequency by that equation. Okay? Any questions about this equation? Does it look familiar? It has a similar kind of expression. Okay, there's an integral with respect to theta and theta minus theta, and the result is a function of omega. It's very similar to this one. It's the first kind of convolution. The first kind of convolution. The expression is very similar. Okay, so let me just copy that equation. So G is going to be, let's say, it's going to be low pass. So let me come up with this notation. Now, this is convolution with a circle. Okay? Convolution with a circle. So basically, it means that the convolution of two spectrum with the frequency domain. Okay, and the notation that I come up with is convolution with a circle around. Sometimes people call this a circular convolution. Circular convolution. Because the convolution happens on the unit circle, basically. And the integral here is from minus pi to, or around the unit circle, basically. Remember that all the spectrum are going to be periodic with respect to every 2 pi, right? And the result of this convolution is also going to be something with a period of 2 pi. Okay, so that's why this convolution is called the circular convolution. And this expression is written over there. Okay? But then what's the feeling? But then, how do we visualize this circular convolution? That's the question. Okay? How would that affect? Because in the end, we care about this magnitude stuff, right? This is the idea we know. This is the ideal response right here. What is this? And what is their convolution? The result of their convolution. That's what we're going to talk about next. Okay? So let's take a look at this. What is the Fourier transform of our window? So there, this Wn is a rectangular window. We know that it's from minus n to n with sample value 1, 1, 1 all the way, all ones from minus n to n, and 0 elsewhere, and 0 elsewhere. This is our rectangular window that's from minus n to n. Its Fourier transform, turns out its Fourier transform, to further confuse you, the Fourier transform is a sinc function in the frequency. Okay. But let me draw a picture first. Okay. Its Fourier transform is going to look like a sinc function. This function, the Fourier transform of a rectangular window sometimes is called the digital sinc. The digital sinc function, which looks like, which has a pattern, okay? Which has the same pattern, but it's also going to be periodic every 2 pi. Alright, so the digital sinc function. This is our Fourier transform of the window function. Okay? And it actually has a closed form. I'm not going to show you the closed form, so it's not that important. I want to just show you that the result, if we have a rectangular window that lasts from pi minus n to pi n, then it's DTFT. It's going to look like that. Having a main lobe somewhere, here you see, and side lobes, and ripples. Let me say, these things can be thought of as ripples. 它有些波浪，有些连接在这里 it has ripples floating around near the main lobe. Okay? Then our question, also, can you make it clear that there's going to be a zero crossing in the frequency in the spectrum. Okay? And so the zero crossing tells us how wide is the main lobe. How wide is this main lobe? This thing is called the main lobe. Main lobe. And main is 主要的指 lobe 花瓣的瓣主瓣。Very well. Okay. So this thing here is called the main lobe. And the width of the main lobe is inversely proportional to the length of time. Okay, so let me make it very clear that the width of main lobe is exactly going to be 2 pi divided by n. That's the width of this main lobe. Wait, I might be wrong. Actually, it should be 2 pi divided by. I'm probably wrong. I'm wrong. I remember it's going to be 2 pi divided by. Should be 2n plus 1. Okay. Anyway, but the key point is roughly inversely proportional to the length in time, because we have 2n plus 1 samples. Right? 2n plus 1 sample, that's the length in the time of length. And this length is going to be inversely proportional to the width and the frequency of the length, with a half width. Okay? So these are like important pieces of information. I want to share with you first, and then we can consider convolution. Now we have one function which looks like sinc, and another function which is ideal. And how about their convolution? How does their convolution look like? What does their convolution look like? That's the question. Okay? So now we are going to circularly convolve these two functions. then what's the result? That's the question. Okay? What's the result? And they convolve circularly. What's the result like? On one hand, we have the ideal response. Okay? Then you draw widely. Remember, ideal response which should cut off exactly at omega c. And on the other hand, we have a, let me just draw a copy of the window transform. Okay? So now this yellow thing here is window transform but shifted to maybe this yellow copy here is the window transform. The Fourier transform of the window was shifted to the frequency speed. Now what is convolution? Convolution means that we're going to flip one of them and shift the other, and just taking the integral of the product. Let me say that again. What is convolution? Convolution is to flip one of the member and then shift the other member and then multiply them and taking the integral. Okay? Now here we're shifting, actually this white thing here should be let's flip the white thing. Okay, let's flip the white thing and then shift the yellow and just calculate that. And let's visualize it. Okay, but in the end, we are going to discuss when we shift the yellow window transform to the left and to the right. And then for every shifting, we shift it by theta and then we stop and take a look to see what's the result of the convolution. And keep shifting. You keep shifting and then wait. No, I'm wrong. So this integral, so just keep my notation, this should be theta. And this should be omega minus. Wait. Oh, I'm just making a mess. I'm making a mess. I'm sorry. Okay, convolution. Let me, I think this time I'm correct. Okay. Oh, shit. Well, about this notation, but you know what? Yeah, let me just explicitly write down the convolution. Sometimes it's just write down the expression explicitly. So that's the definition. Okay, so in this integral result, I should say, actually, even better, we should say the result is going to be W circularly convolved with low pass, and the result is a function of omega. That's a better way of writing it. As the way once I was suggesting that whenever we talk about convolution of two signals in terms of length, that's the better way of writing that. Better way of expressing it. Okay? So anyway, so the result convolving two spectrum is going to be still a function of omega, right? And the exact expression is that, right? So I was trying to suggest that we are going to shift one, flip the window transform. Flip it. So here is the window transform as a function of theta. So we have already flipped it and then shifted by omega. So that was one of our omega. Okay? And made a lot of mistakes. But hopefully now this time is correct. We're going to shift it in the theta domain. And then the flip it is theta domain is shift by omega. And then multiply this thing, that's it. And multiply it with our ideal response, which is the function theta and is going to be 1 from minus omega cutoff frequency to cutoff frequency. That's the ideal response. And 0 elsewhere. And we're going to shift this window transform to the left and to the right and see how this integral varies as a function of omega. That's the result of our convolution. Okay? Right? So hopefully you can just visualize when we shift this yellow thing to the left and to the right. Okay? To the left and to the right. So it turns out that when this yellow copy, this yellow, I call it window transform because it's the first transform of our window. Okay? So this copy of the window transform is far away from the cutoff frequency. When it's far away from the cutoff frequency, then this result of this integral is almost constant. So I'll draw the result in, let's say, in green. Okay. So if this is the cutoff frequency, and when this yellow thing, when omega is far away from the cutoff frequency, and we shift it a little bit to the left, a little bit to the right, the result should not differ much. Okay? So let's say that when omega is far away from that cutoff, the result should be a constant, nearly a constant. Maybe it can go up and down a little bit, but not too much. Okay? But also when this another situation when this omega is far away from the cutoff frequency, but in the stop band. The result of our integration is nearly 0. It's going to be nearly 0. Okay, so we move this a little bit. When the result is far away from the cutoff frequency, but in the stop band, the result is nearly 0. You can go a little bit up and down, but the result is nearly 0. So now you probably figure out, make a guess that the result near the cutoff frequency is going to be more interesting. Okay? The result near the cutoff frequency, when this yellow thing is moving from the left to the right and crossing that boundary, crossing that cutoff frequency all the way and keep moving to the right. That's more interesting. Okay? Let me show you the result. The result is that you will see ripples. Okay? You're going to see ripples. Near the cutoff frequency, there's going to be some ripple, and the result is we say is the response is going to make a transition from the pass band to the stop band. It's going to make a transition to the pass band from the pass band to the stop band. And this is the idea. This is the property, the kind of concept of convolution and frequency domain. Okay. So to summarize, we have I suggest that our design is going to have the first step, which is just keeping the middle part. And by keeping the middle part, we are multiplying the ideal response by a window, by a rectangular window. And consequently, in the frequency domain, their Fourier transform is going to be convolving. And what is convolving? Convolving, the result is going to be that the resulting frequency is going to make a transition from the pass band to the stop band. And near the transition frequency, near the cutoff frequency, is going to be, there are going to be ripples. Okay, so next time we talk about how high is the ripple and can we improve on it? Perhaps by keeping more and more in ripples, for example. By increasing the length of the window, how much can we cover? How much can we approach that idea? Right? So that's so we keep talking about this new topic, FIR filter design, next time we meet on Thursday. Okay? So thank you for coming in, and please make sure that you turn in your homework before you leave. Thank you.